Fine. Let's start. Number 11. Planet 9 is a black hole. Out past Neptune, in the cold dark where sunlight is just another star, something is pulling on the orbits of the most distant rocks in our solar system. A handful of icy worlds out there are tilted and clustered in a way that shouldn't happen by chance. For years, the leading explanation has been a hidden ninth planet, a few times the mass of Earth, drifting unseen in the black, a planet we've simply never caught. But in 2019, two physicists, Jakob Schultz and James Unwin, asked a different question. What if it isn't a planet at all? What if the thing bending those orbits is a primordial black hole? A black hole left over from the first instance of the universe, only a few Earth masses heavy, quietly captured by our own sun. Here's the part that gets under your skin. A black hole of that mass wouldn't be some yawning cosmic pit. Its event horizon would be about 5 centimeters across, the size of a grapefruit. You could, in principle, hold the mass of 5 Earths in your 2 hands, except you couldn't, because it would be the densest thing for light years, and it would kill you, in a way physics barely has words for. And if it's real, it would be, by an enormous margin, the closest black hole to our planet. Not thousands of light years away, in some distant nursery of dead stars. Right here, in our neighborhood, sitting in the dark between us and the edge of the sun's reach. How would you even find it? You don't. Not directly. The idea is to look for a faint halo of dark matter around it, annihilating into a whisper of X-rays and gamma rays against the black. A shadow with a glow. We used to think we'd mapped our own solar system, that the surprises were all out there, in other galaxies, around other stars. And now, there's a serious paper suggesting we might have a black hole in the family and never noticed. The next generation of telescopes should tell us whether it's a planet, a black hole, or nothing at all. Until then, the outer solar system keeps its secret. And somewhere out there, something small and heavy and utterly silent keeps tugging on the dark. Number 10. The speed of light wasn't always constant. There is one number physics treats as sacred, the speed of light, roughly 300,000 kilometers per second, the cosmic speed limit, the constant that shows up in nearly every equation that matters. It's the closest thing we have to a law that never bends. Nothing outruns it. Nothing changes it. Except maybe it did. In the late 1990s, physicists João Magejo and Andreas Albrecht proposed something close to heresy. What if, in the first sliver of the universe's life, light traveled far faster than it does now? Not a little faster. Vastly faster. And then slowed to the value we measure today. It sounds like a wild swing, but there's a reason serious people took it seriously. Cosmology has a couple of stubborn puzzles. Why is the universe so uniform? The same temperature in every direction, even in regions that should never have had time to touch. The mainstream answer is inflation, a burst of impossibly fast expansion in the first fraction of a second. But a varying speed of light solves the very same puzzles by a different route. If light was quick enough early on, those distant regions could have communicated after all. They could have evened out. And here's the thing that lifts this above idle speculation. It's testable. A varying speed of light leaves a slightly different fingerprint in the pattern of ripples from the early universe than inflation does. We can look. We can measure. The data can actually decide between them. Sit with what the idea implies, though. If the speed of light can change, then the constants we build reality on aren't eternal. They have histories. They were something else once. The floor under physics stops feeling like bedrock and starts feeling like weather. Most cosmologists still bet on inflation. It fits what we see, and tampering with the speed of light breaks symmetries that experiments guard closely. But the proposal hasn't gone away, because the question underneath it won't go away. We measure the universe with a ruler and a clock, and we assume they've always been the same ruler and the same clock. What if they weren't? What if the rules we're using to read the past quietly changed somewhere behind us, and we never felt it happen? Number 9. There was no Big Bang. Ask almost anyone how the universe began, and you'll get the same two words: Big Bang. A single hot, dense point, 13.8 billion years ago, that erupted into everything. It's the origin story we all grew up with. The first moment. Time's starting line. Now here's a theory that quietly erases it. It's called gravity's rainbow. The idea is that particles of different energies experience spacetime slightly differently. Light of different colors, moving through the same gravity, takes marginally different paths. It's strange, but it's a real line of research. And when a team led by physicist Adel Awad applied it to the whole cosmos, they found something that stops you cold. Rewind the universe under rainbow gravity, and the singularity disappears. As you run time backward, the universe gets denser and denser, approaching an incredible concentration, but never quite reaching the infinite point that a true Big Bang requires. In one version, the density climbs forever without arriving. In another, it levels off at a huge but finite value and just sits there. Either way, there is no first moment. There is no beginning to find. Let that settle. It doesn't move the birthday of the universe earlier. It removes the birthday entirely. The cosmos in this picture has always existed, stretching backward into time without end. No creation event, no starting line, just an infinite corridor of past, receding forever behind you. There's something almost worse about that than a violent beginning. A Big Bang is terrifying, but at least it's an edge, a place where the story starts. An eternal past has no edge at all. You can keep asking what came before, and the answer is always more, and more, and more. Now, honesty matters here. Rainbow gravity is speculative. It isn't a finished, tested theory, and letting spacetime depend on energy creates problems of its own. There's no observation yet that proves the Big Bang didn't happen. But the fact that the math even allows it, that you can write down a universe with no beginning and have it hold together, is the unsettling part. The origin of everything might not be an origin. It might just be a horizon we can't see past. And behind it, no wall. Only more dark, going back forever. Number 8. Space loses dimensions. When you look closely. You live in 3 dimensions of space. Length, width, height. Add time, and you get the 4-dimensional spacetime that general relativity describes. This feels about as solid as facts get. You can move left, right, forward, back, up, down. 4 dimensions. Done. But zoom in. Keep zooming. Down past atoms, past nuclei, down toward the smallest scale physics can even talk about, the Planck scale. And according to one of our best attempts at a theory of quantum gravity, something quietly horrifying happens. Space starts to lose dimensions. The approach is called causal dynamical triangulations. Instead of assuming what spacetime is, you build it out of tiny simple pieces and let the geometry emerge from the simulation. And when physicists Renat Lal, Jan Ambjörn, and their colleagues ran it, they found that spacetime looks reassuringly 4-dimensional at large scales, the world you know. But as you probe smaller and smaller, its effective dimension smoothly drops. Down toward 2. At the finest grain of reality, space behaves as if it has roughly 2 dimensions instead of 4. The smooth, roomy world you trust thins out into something flat and strange the closer you look. And here's the detail that turns a curiosity into a chill. This isn't a quirk of one theory. Several completely different approaches to quantum gravity, built on different assumptions by different people, independently predict the same thing. Dimension falling toward 2 at the smallest scale. When unrelated roads all arrive at the same odd destination, physicists start to suspect the destination is real. Think about what that means for the ground under your feet. The continuous, seamless space you move through. The space that feels infinitely divisible and endlessly smooth may be a large-scale illusion. A comfortable average. Underneath it, at the level where reality is actually stitched together, space is fraying into something you have no intuition for. We treat the world as a stage. Fixed, dependable, always there. This says the stage is only smooth because you're standing too far back to see the threads. Now, to be fair, the dimension being measured here is a subtle, effective quantity, not necessarily the plain count of directions you can point. And none of this is confirmed by experiment yet. But the picture lingers. Look closely enough at nothing in particular, at an empty patch of space, and it stops being the space you thought it was. Number 7. Gravity isn't real. Right now, a force is holding you to your chair. Gravity. The oldest, most familiar force there is. Newton described it. Einstein reimagined it as the curving of space-time. It's the one force you feel every second of your life without thinking about it. What if it isn't a force at all? What if it isn't even fundamental? That's the claim of physicist Eric Verlinde. In his picture, gravity is what's called an entropic force. It emerges from information, from the way the universe keeps its books about where things are. The idea leans on deep results about black holes and thermodynamics, where entropy and information turn out to be woven into the fabric of space itself. And out of that bookkeeping, Verlinde argues, gravity falls out, not as a thing pulling on you, but as a statistical tendency, the way heat flows, or the way a stretched rubber band wants to snap back. Emergent, secondhand, an echo of something more basic. If that were the whole story, it would already be unsettling. But Verlinde pushed further. In 2016, he showed that his emergent gravity naturally produces the extra pull we normally blame on dark matter. The mysterious invisible stuff that's supposed to make up most of the mass in galaxies. In his framework, you might not need it. The missing mass isn't matter at all. It's a feature of how gravity emerges. Sit with the size of that. For decades, physicists have built detectors, drilled into mountains, waited in the dark for a single dark matter particle to reveal itself. If Verlinde is right, they were hunting something that was never there, chasing a ghost conjured by a misreading of gravity itself. And then there's the personal version of the vertigo, the force pinning you down, the weight in your limbs, the reason you don't drift off the surface of the earth. It might not be a fundamental push from the universe. It might be a kind of statistical pressure, an emergent nudge from information you can't see and will never touch. Most physicists still favor dark matter. Verlinde's gravity struggles with galaxy clusters and with the oldest light in the sky, and standard cosmology fits those better. It's a minority path, but every time you stand up and feel your own weight, there's now a theory whispering that the most solid sensation you own might be a rumor the universe is telling itself. Number 6. The fate of the universe just changed. For most of this century, we thought we knew how the universe ends. Dark energy, the mysterious pressure pushing everything apart, was assumed to be a constant, a fixed property of empty space, never changing, never tiring. And a constant dark energy gives you one ending: expansion, forever accelerating, galaxies sliding out of view one by one until the sky goes dark and cold and empty. The big freeze. A slow, quiet, endless fade. Settled. Depressing, but settled. Then, in 2024 and 2025, the numbers moved. An instrument called DESI, the Dark Energy Spectroscopic Instrument, built the largest three-dimensional map of the universe ever made. Nearly 15 million galaxies and quasars, tracing how the cosmos has expanded across 11 billion years of history. And when the DESI team combined their map with the oldest light in the sky, with exploding stars, with the way galaxies bend light, They saw something nobody wanted to bet on. Dark energy might not be constant. It might be weakening. If that holds up, it tears up the ending we'd written. A dark energy that changes with time is a completely different story than one that stays fixed forever. The tidy eternal freeze stops being guaranteed. And here's the thought that follows it into the dark. If dark energy can weaken, then in principle, it could one day reverse. The eternal expansion everyone treats as destiny might be nothing more than the phase we happen to be living in. Nobody's ending the universe on a press release. This isn't confirmed. It's a hint, strong in some combinations of data, softer in others, and it leans on measurements that could still hide a mistake. A plain, boring cosmological constant is still on the table. But think about what just happened. The fate of everything, the final chapter of the entire cosmos, was something we spoke about with confidence. And a telescope full of galaxies quietly reminded us we were guessing. The ending isn't written. We just assumed we'd read it. And the universe, as always, hadn't agreed to anything. Number 5. The universe manufactures observers. Most cosmic horror comes from indifference. The universe is vast, cold, and doesn't know you exist. That's the usual dread. Here's a theory that flips it into something stranger and, in its own way, worse. What if the universe isn't indifferent at all? What if it's aimed? Aimed at building things like you. The theory is called assembly theory, developed by Sarah Walker and Leroy Cronin. At its core is a simple, sharp idea. Every complex object carries a history. You can measure how many steps it takes to build that object from basic parts, a number they call the assembly index. A rock has a low index. A protein, a circuit, a living cell, those have enormous ones. And crucially, complex things only exist in large numbers when something is selecting for them. Assembly theory turns that into a measurable quantity. It lets you look at an object and read how much history, how much causation is packed inside it. That alone is a striking claim. That complexity leaves a physical fingerprint you can measure in a laboratory, but the deeper version goes further. In its strong reading, assembly theory treats time not as a passive backdrop, but as a physical thing, a dimension that grows, with the universe using it to stack complexity higher and higher. Selection and evolution stop being biology's private business and become features of physics itself. Follow that to the end. If the cosmos is genuinely driven toward building complex things, then observers, minds, creatures that look up and wonder might not be a lucky accident on a damp rock. They might be something the universe was always going to produce. Not because anyone planned it, because that's the direction the machinery runs. There's a particular unease in that. It's one thing to be an accident in an indifferent void. It's another to suspect you're an output, a thing the universe was assembling all along, whether it noticed or not. And I should be straight with you. Assembly theory is contested. Serious critics argue its central measure collapses into ideas we already had, ordinary information and compression, and that the grand claims about time as a dimension are reaching too far. It's frontier science, still fighting for its footing, but the image it leaves behind is hard to shake. A universe that doesn't just permit complexity, a universe that builds it and keeps building until something is standing there, complicated enough to ask why. Number 4, there is no shared reality. You and I are looking at the same object. It has properties, a position, a state, a definite way of being. We might describe it differently, but underneath there's one true fact of the matter, one shared reality we're both sampling. That assumption is so basic, you've probably never once questioned it. Quantum mechanics might be about to take it from you. The idea comes from physicist Carlo Rovelli, and it's called relational quantum mechanics. Its claim is deceptively quiet. There is no absolute, observer-independent state of a system. Properties don't belong to objects on their own. They exist only in relation to whoever or whatever is interacting with them. The state of a particle for you and the state of that same particle for me are not required to be the same thing. And there is no God's eye view above us both to say which is correct. Because in this picture, there isn't one. For a long time, you could wave that away as philosophy. Clever wordplay about measurement. But then the experiments arrived. Versions of a thought experiment called Wagner's Friend, where one observer measures a system and another observer measures the first observer. Under a few reasonable assumptions, these setups predict that the two observers can end up with genuinely contradictory records of what happened, both complete, both correct, and impossible to reconcile. Laboratories have actually run versions of this, with photons standing in for observers, and the results line up with the unsettling conclusion. Objective facts, the kind everyone can agree on, might not survive at the quantum level. Think about what that quietly dissolves. Not just particles. The idea of a single shared world. The comfortable belief that there is one reality, one set of facts, and we're all just looking at it from different chairs. Relational quantum mechanics says the facts themselves are relative. Yours are yours. Mine are mine. And the universe never promised they'd match. It's an interpretation, one of several, and it doesn't change a single prediction quantum mechanics makes. Other physicists keep their objective reality by choosing different interpretations, and that's a live debate. But the door is open now. Somewhere in the foundations of physics is a serious, tested adjacent idea that says the shared world you take for granted, the one solid thing everyone stands on, may not be there at all. Only a crowd of separate views, agreeing most of the time, right up until they don't. Number 3. You were born impossibly early. This one is going to feel like it's about the whole universe. It's not. It's about you. Specifically, it's about why you exist right now, at this particular moment in cosmic history, and why the math thinks that's deeply wrong. Start with eternal inflation. It's a leading idea about the big picture, and it says our Big Bang wasn't the only one. That the larger cosmos is constantly, forever, sprouting new universes, pocket after pocket, at a staggering exponential rate. It never stops. It's still doing it. And here's where it turns on you. If universes are being created exponentially fast, forever, then at any given instant, there is vastly more brand new cosmos than old cosmos. Try to count where a typical observer should find themselves, and the numbers stampede in one direction. Almost every observer, in almost every pocket, should exist at the earliest possible moment their universe allows. As early as physics lets a mind form. This is the youngness paradox, wrestled with by cosmologists like Alan Guth, Alexander Vilenkin, and Raphael Busso. And the punchline is uncomfortable. By this counting, you should have opened your eyes into a universe far younger and hotter than this one. You should be among the very first observers, not sitting here almost 14 billion years in, surrounded by settled galaxies and cooled-off starlight and the long, comfortable aftermath of creation. But here you are, late, impossibly, statistically late, existing in a mature, quiet, structured cosmos that, according to the naive math, almost nobody should ever get to see. So one of two things is true. Either our way of counting observers across an infinite multiverse is broken, which is what most cosmologists actually believe. The measure problem, they call it, the honest admission that we don't yet know how to do probability when there are infinitely many of everything. Or the counting is fine, and your existence, right here, right now, is a fluke so extreme it should barely be allowed to happen. Neither answer is comfortable. One says our best theories can't even count us. The other says you're a statistical impossibility reading this. And the universe, sprouting endlessly somewhere beyond our horizon, isn't offering to explain which. Number 2. The universe is a neural network. You've heard the simulation idea. That reality might be a program running on some vast computer built by someone, somewhere. It's a good scare. But there's a stranger cousin of it, and this one doesn't need a programmer. It doesn't need anyone at all. In 2020, physicist Vitaly Vanchurin published a paper with a title that sounds like science fiction and reads like serious physics. The World as a Neural Network. Its proposal is exactly what it says, that the universe, at its most fundamental level, beneath particles, beneath fields, beneath space-time, is a neural network. And it is learning. Not a network someone built to simulate us. The network is the reality, the bottom layer. And Vanchurin showed something remarkable to back it up. If you take a huge neural network and watch how it behaves as it learns, the mathematics that describes it starts to look like the mathematics of physics. Under certain conditions, the equations of quantum mechanics emerge from it. Under others, the equations of classical physics, the world of everyday motion, emerge too. In other words, the two great pillars of physics, the quantum and the classical, might both be approximations of one thing underneath. A learning system, adjusting itself, settling toward better and better states, the way a network tunes its connections while it trains. Here's the part that gets into your chest. This didn't come from mysticism. It came from noticing that the math of machine learning and the math of physics keep colliding, keep echoing each other in ways that feel like more than coincidence. And unlike a lot of grand cosmic claims, Vanchurin framed his as something that could, in principle, be tested and proven wrong. So sit inside the idea for a moment. If it's right, the laws of physics aren't fixed commandments. They're what a learning process looks like from the inside. The constants, the forces, the unfolding of time itself, all of it the behavior of a vast mind slowly teaching itself something. And you, your thoughts, this moment, the fact that you're following these words. Not the audience of the machine, not even a simulation inside it, a passing pattern in the network, a ripple in something enormous that is busy learning and has never once needed to know that you are here. It's speculative. Most physicists file it under fascinating, not established, and the word network may be carrying more weight than the math has earned. Fair enough. But every theory of everything we chase assumes there's a final law at the bottom, a last equation. This one says maybe there's no equation down there at all. Just something learning. Forever. And we are the thoughts it hasn't finished having. Number 1. The last event in the history of everything. Every scary thing we've talked about still assumes the show goes on. Stars, galaxies, time itself, grinding forward. So let's go all the way to the end. Not close to the end, the actual end. The final event that will ever happen, after which nothing happens again. To get there, we lean on Freeman Dyson, one of the great minds of physics, who in 1979 looked further into the future than almost anyone had dared. Past the death of the sun. Past the last star burning out. Into an era so distant the numbers stop being numbers. Here's the setup. Assume protons are stable, that they don't quietly decay, which is still an open question. Then, the universe's final residents are black dwarfs, the cold, dead cinders of stars, dark and frozen, drifting in an empty cosmos. You'd think they'd just sit there forever. They don't. Inside them, quantum tunneling is at work. Given enough time, and there is nothing but time, atomic nuclei slowly fuse, creeping toward the single, most stable form of matter in existence. Iron. Not the iron in your blood, or your buildings. Iron 56, the most tightly bound nucleus there is, the place all matter rolls downhill toward if you wait long enough. Over unimaginable stretches, every dead star turns to iron. The universe becomes a scattering of iron stars in the black. And how long does that take? Roughly 10 to the power of 1,500 years. Let me try to make that land, and I'll fail, because it can't be done. Write a 1, then 1,500 zeros after it. The current age of the universe is about 10 billion years. Against that final number, the entire history of the cosmos so far, every star, every galaxy, every life rounds to zero, to nothing. It hasn't even started, and it doesn't stop at iron. Given even longer, those iron stars collapse, some into neutron stars, some into black holes. And those black holes evaporate too, bleeding away into faint radiation over spans that make the iron era look brief, until there is nothing left with structure, no stars, no matter as you know it, no events. That is the last thing that will ever happen. The universe slowly, patiently, converting itself into iron and then into dark, and then falling silent for a length of time so long that the word forever finally becomes accurate. We spend our lives worried about what comes next. Here is the answer at the largest possible scale. Eventually, nothing comes next. The cosmos runs out of things to do. And in that endless, iron-cold quiet, the strangest thought of all is this. For a brief, impossible flicker near the very beginning, some of that matter woke up and looked around and understood exactly where it was going. That was us. That is now. And it is the most extraordinary thing the universe will ever do. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.